We shall look at the crevice corrosion of metals and in details today. Before we start discussing about the crevice corrosion further, it will be worthwhile to recollect what we have been discussing on crevice corrosion. Okay. So recap. Now, we looked at the mechanism, right. First of all, the crevice corrosion, the origin of that is due to the formation of a crevice, which can happen because of, let us say, when you have joints in the metal structures, such as a flange joint or a rivet or an expansion joint or threaded joints, as you see in the fasteners. These are coming out of the design parameters. Okay. It can also arise out of the other reason, where like you have some deposition taking place because of the environment, isn't it? We also call that as under deposit corrosion taking place. So these are the factors that leads to the formation of the crevice. Now, why does the crevice corrosion occur? Can anybody recollect? What is the basic requirement? Yeah? Is that the primary reason for that? Huh? Yeah?
High corrosive environment like chlorine, presence of chlorine.
Is that what it is? What is the primary reason? Why does it start primarily in crevice corrosion? So, the formation of the differential aeration cells, right. The basic is that there is a concentration of oxygen between the two locations, starting point. So, the point is that the starting point comes because of differential aeration. Why would the differential aeration lead to this problem? First of all, what kind of metals the crevice corrosion occurs? The passive metals. So, only in the passive metals, so called passive metals, the crevice corrosion occurs. So, in such a situation, what is the role of differential aeration? Means what? For example, there are locations where the oxygen concentration is very high, there are locations where the oxygen concentration is very less. So, what happens due to this? Yeah?
Iron might decrease or increase.
The limiting current density may be, yeah, the limiting current density might increase when the oxygen concentration is more. So, what happens?
We may transfer from passive to active.
Which one? Suppose you have more limiting current density, will it become active or passive? Passive. So, when you have higher oxygen concentration, the metals tend to become passive. The one where the oxygen concentration is less, the metal tend to move towards active potentials. So the crevice starts corroding over a time period, because again we say that it is diffusion controlled. When you say crevice, it's no convection, right? The dimension is so small, there is no convection, and so the diffusion process, and so the oxygen within the crevice with the time steeply decreases, and so that becomes an anode. That is the starting point of that. So what happens again in the crevice? Why would the corrosion so in the crevice, what drives the crevice? What is the difference between a crevice and the outside the crevice? One is oxygen concentration to start with happens, okay. Subsequently what happens? When the corrosion proceeds, the crevice establishes its own environment different from what you find externally, right. So it establishes an environment, so it's a localized environment. If you can browse through your notes, you will see that, right. In the crevice, what is happening over a time period? You will see that what happens? It creates an acidic environment. If the environment has chlorides, the chlorides migrate towards the crevice. So here what happens? The pH drops significantly, and you have chlorides, so the passive metals, they start depassivating actually, okay. It becomes totally active. So corrosion occurs. So it establishes a localized environment which is different from the external surfaces, because external surfaces are open, there is a convection taking place, and so there is the pH is not going to drop at all, okay. So the localized environment, that is the reason for that. So this leads to growth and stability of the crevice. So we have seen these factors, right. Since it's a crevice, what happens? That is no or poor convection, okay, of the electrolyte. So migration only due to what? Migration only due to diffusion. So this is it's a kind of basic mechanism we saw in the last class. Now we know that this is an industrial problem, that we need to find a solution to the problem. In order to find a solution to the problem, you must know what are the factors or the parameters that affect the crevice corrosion, right. So you need to understand, it is very interesting that the foremost important factor is the crevice itself. So geometry of the crevice, one important factor. Second factor is the environment. course, when you have an environment, it also decides the electrochemical factors. Okay. The fourth, metallurgy of this, right. So, these are the factors broadly I would say that influence the crevice corrosion of metals, right. So, let us see this in details. One after another. Let us take the crevice. When I say crevice, I was meaning that it's a geometry. Why the geometry must be important? Yeah. Why should the geometry important? That's right. Because the crevice corrosion more often is a transport control, and the transport through the diffusion process. So, the geometry will play important role because that is going to decide the how the diffusion will occur within the crevice. Okay. In fact, you would notice that the metal dissolution for, okay, in fact more resistant metals, more corrosion resistant metals become susceptible to crevice corrosion. So, it's no wonder that some cases the corrosion occurs, some cases corrosion does not occur. The environment may be the same, but if the crevice geometry, the crevice dimensions change, then the extent of crevice damage could change. Okay. For example, I would say 904L is a stainless steel. Okay, it has let us say 20% chromium and 25% nickel, 4.5% molybdenum and 1.5% copper. It's supposed to be far better than 316, 317 stainless steels. Okay, you see the high amount of nickel, high amount of chromium, but it is prone to crevice corrosion. But 7030, what is this? This is a copper nickel alloy, is not prone. Aqueous corrosion. It's a very interesting thing. Okay. Now let's take a crevice and see what kind of dimensions will affect the crevice corrosion, right. One dimension is the crevice width, right, and this is the crevice length, right. Suppose I have an environment here, this side, where will the crevice corrosion occur, and will the depth of attack is going to be same throughout. Okay. So, you need to look at this. Let us look at this, and you please tell me okay. Let us take the W width. If the width is increasing, what will happen to crevice corrosion? Yeah, the crevice corrosion will decrease. So, with increases the crevice corrosion, why does it happen? Yeah, the stagnancy is reduced. In other words, there can be more convection, right. So, because of that the oxygen concentration within the crevice would increase if the width of the crevice is increasing. This is an irony of that, right. If you talk about a flange joint, suppose I take a flange and joint, like suppose I take a flange joint, right, suppose I make a flange, you guys might have known the flanges, right. Suppose there is a flange joint, suppose I want to tighten this out. From the mechanical engineering point of view, what do you expect to happen? You expect that the gap should be decreasing, then only it is going to be leak proof, less vibration. So, typically these mechanical joints are expected to be as tight as possible. The crevice width has to be as small as possible, then only that becomes an effective joint, otherwise it becomes a leak, right. So, that means inherently the good joints will suffer more crevice corrosion than joints which are looser, but you can't help it, you have to have tight ones, right. So, this is a real problem in practice. So, width is an important one. If the you can also talk about other one, a metal and a metal interface. Okay, 1, 2, a metal and a non-metal interface. Like for example, a rubber, for example, okay. Which of the two joints will suffer more corrosion? I have a metallic gasket, I put other way, I have a metallic gasket, and other case I have other rubber gasket. Corrode more, you are right. Why do you think so?
Chances of pores being or some water or air being trapped inside.
Yeah, I mean the just I mean it's right. I mean rubber will have problem, but that what is the reason for that? Suppose if I were to tighten this, right, with a metal and metal and metal and rubber, what will happen from the point of view of this crevice width? Where the more where the width of the crevice is more, metal and metal or metal and rubber? So the crevice dimension also depends upon what kind of joints you are going to have. And metal and rubber, the crevice gap is going to be small, and so you would have more crevice corrosion compared to metal and metal skins. Okay, so the two suffers more. Let us take the other effect of that. Now here is the environment. This is the length through which where do you think the crevice corrosion here will be the more? This is the crevice, right? This is the crevice. Where do you think the crevice corrosion will be more? Yeah, in the middle. Okay. Alright. So at least you can say that the crevice corrosion at the mouth of the crevice is not going to be there at all. Why do you think so? The oxygen, there will be reasonable amount of oxygen present there, crevice mouth will be passivated, right. So here you find will be passivated, right. Why? Because the oxygen partial pressure is okay, is good. The oxygen partial pressure decreases from the mouth to the interior, and after some time it becomes almost, it is not going to vary at all, right. So what will happen is that crevice mouth is going to be a cathode, and all these areas are going to be the anode. Now the cathode drives the corrosion of the anode, right, isn't it? The cathode drives the corrosion of the anode. Now what also can happen is that if the distance between the anode and cathode is increasing, what will be the effect of cathode on the anode? Keeping other parameters same, right, keep other parameters same, okay, assume that the chemistry of the electrolyte inside this crevice is same, and this is the anode and the cathode, but if I move away from here inside, what will be the effect of this cathode on the anode? The cathode drives the anode, right, and because there is a potential difference between the anode and the cathode, right. So that is, this is going to be relatively positive and this is going to be relatively negative. Now when I start moving from here to this, what will happen to this driving force? It will decrease, right. So the corrosion rate decreases because of this, okay. The corrosion rate due to cathodic influence decreases. But the oxygen concentration, what about oxygen concentration? The oxygen concentration in this case, concentration decreases, right, from here to this, but the potential, driving potential decreases. So that means somewhere in between you are going to have high corrosion rate, after that the corrosion rate will start decreasing. So you will find that somewhere here, okay, more attack, because as you move away from this, the effect of the cathode on the anode decreases. So it is like galvanic cell, right, galvanic corrosion, right. So you will have more just below the mouth of the corrosion. So this leads to, okay, just below the mouth of the crevice corrosion, okay, the corrosion is more. Now that depends upon what? That depends upon the of the electrolyte. What is rho? Rho is equal to resistivity of the electrolyte. It's a very interesting one, you know. The resistivity is 0, then also there will be no crevice corrosion. Resistivity is too high, is confined to the mouth of this actually, okay. So essentially it depends upon the resistivity of the electrolyte as well. So put it in simple terms, the oxygen concentration decreases from the mouth, the interior, the galvanic interaction between the cathode and the anode decreases from here to this. So there are two opposing factors, somewhere in between maximum crevice corrosion occurs. So this is an important one, okay. So that is why if you just look at some data, so this is a typical gasket corrosion, okay, and this is your stainless steel clad, this is of course a steel the shell here is cladded with a stainless steel. Now it is here you have the environment, right. You see the attack here, the attack is happening somewhere here, right. It does not happen too far away, it does not happen very close to it does not happen at the mouth, it happens somewhere in between. So the crevice corrosion normally occurs below the mouth of the crevice because that is optimized sensation taking place, because you need a electrochemical driving force between the cathode and the anode on one hand, the other hand the oxygen solubility also the content of oxygen also decreases as you move from the mouth of the crevice to the center of the crevice. So that's how you see that the crevice corrosion always occurs below the mouth of the crevices. I hope you understand, and this one is very important actually, okay. Yeah. You are talking about this one or another? Yeah. Yeah, this is no, see it is a shell actually, the shell, it is not a tube, it is a shell. Yeah, this is a gasket, no, I mean, see, this is the, in a heat exchanger, in a heat exchanger, if you just look at the heat exchanger, not good, okay. This is called what? This is called as a header or shell, and you have not exactly right here, you will have of course tubes. All these tubes are going over like this, okay. So this is the, what we are seeing here is this joint, So this, what you are seeing here is this joint, okay. It is a flange, you see these are places where you put the bolts and you fasten that actually, right, okay. So it is a header that has suffered the corrosion, and okay, and through this what happens now, through this you have a seawater, right. Now the seawater here is flowing through the cell side, the tube may be some other process liquid, no, it may be some hydrocarbon or whatever that flows into that actually, okay. So here the coolant is the seawater, that seawater is flowing through the headers, yeah, and then through the shell, and the tube, I think there are some process liquid in the of in a given refinery actually, okay. So what you are referring is this joint, okay, which is a flange joint taking place this. Is it fine? Yeah. the corrosion has occurred because of seawater. Because of seawater, this was cladded with 2507 2 plus grade stainless steels. Okay. You will see later that when you talk about pitting corrosion, this duplex stainless steel has got high resistance to pitting corrosion. Okay, what it is actually. And you clad it because you can't use a whole thickness of duplex stainless steel, is expensive, right? You just go for a 3 millimeter clad because the basic carbon steel is cheaper for us to do that. So that is about the crevice. The next important thing is the environment. Okay. When you say environment, we normally refer the bulk only. We are not referring the environment in the crevice, because the environment in the crevice is generated by the crevice by itself. That depends upon the metal you are dealing with. Of course, it has a bearing with the bulk electrolyte, okay, but still you could have vastly different electrolyte in the crevice as compared to the electrolyte composition in the bulk actually. Okay. So, when you look at the environment, it is the oxygen content, pH, chlorides present in this actually, the temperature, okay. If you want, you can add agitation or otherwise. The other related parameters, what is that? Like diffusion, convection, but all interrelate to each other, okay, and biological factors. When I say biological or fouling, you can put the word fouling actually. Generally, we can say that when you decrease the pH, crevice corrosion increases. Similarly, the temperature, crevice corrosion increases. Chloride, crevice corrosion increases. Which one? Yeah, there may be some diffusion increasing, okay, but that is not going to be commensurate with the passive film destruction. The passive film would destroy. In fact, if you look at titanium, let's take this case of titanium. Titanium in ambient seawater resistant to crevice corrosion. If you rise the temperature at high temperatures, titanium is prone. The reason being the chloride attacks the film, the passive film, and exposes the bare metal, and so what happens? The crevice corrosion occurs. So we will see this, the role of metallurgy in crevice corrosion we see later. How does the metallurgy of the alloy can influence the crevice corrosion, we can see later how, I mean those things we will see later. But at this point it is sufficient to understand that the passive film stability depends upon the temperature in addition to the environment. Chlorides attack the passive film. If you rise the temperature, the pitting potential drops significantly. So, the film gets damaged and so metal becomes active. So, there is going to be crevice corrosion occurring. Essentially, in the crevice, if you are able to make the metal passive, very stable, then what happens? You may have differential aeration, but still you will not get a crevice corrosion at all, right. So, the crevice corrosion also depends upon, in addition to deaeration and all, but if the metal can be made inherently resistant to corrosion, then the crevice corrosion resistance can be very high, possible to do that, okay. So, that is why the metallurgy is being developed actually, okay. So, titanium generally is very good, is seawater application, no problem, does not pit and all, but the temperature is increased. What does it mean? Assume that I use an heat exchanger in a seawater is used to cool the heat exchangers, right. Suppose the temperature of the seawater is, I would say, 70, 80 degrees Celsius or maybe 100 degrees Celsius, probably the titanium will also start undergoing crevice attack, or the temperatures, or in some situations where it is not necessarily seawater, it can be a gas turbine operating in the naval ship or ship, for example, you use titanium alloys, and then if salts go and deposit, the temperature of these components 120, 200, 250 Celsius, they undergo crevice corrosion. So, the crevice corrosion would also depend upon the stability of the passive film, and that depends upon the environment, pH. In fact, same thing, if you lower the pH, the passive film stability comes down. So, crevice corrosion is now increasing at all. So, they are of course interrelated to each other, that we can say, okay. So, these are the parameters. The other important parameter in the solution is the resistivity. So, very interesting thing, resistivity is a very interesting one. We just made a very passing remark earlier, right. Look at the resistivity. Let us take the case of, I think you guys are all familiar with the polarization curves of if the oxygen concentration is more, start passivating. If the oxygen concentration is little less, right, this is the Crevice mouth and this is your crevice. Can I say that? Okay. So, what does it mean? So, this is the place where the potential is, let us say, relatively negative, place potential is relatively positive, okay. This corresponds to this, corresponds to this, correct or not? What moves the potential from here to this? It is oxygen that makes the potential to move from here to this, right. If I have an external cathode, if I raise the potentials, can this move up or not? Assume that there is no oxygen present, if I have an external cathode, I apply a voltage, can this move up or not? That is what you do in anodic protection, right, you just move it. So, that means if this is the cathode, can this cathode make this anode to move up to this? Can it move? In principle, yes, right. If I have a same metal, one is positive, another is negative, this guy will start lifting this up and this guy will start lifting this down, right, moving down, both are possible, right. if this guy has to have negative here, positive here, then there has to be resistance between these two, between these two places there has to be resistance. The resistance is 0 or less, what happen now? The anode and cathode will become almost like similar only. So this guy also start passivating in principle possible. That means the resistance of the electrolyte is very important. If there is no resistance, substantial resistance, the crevice corrosion will not exist. One of the reasons why crevice corrosion occurs is that it happens in the low resistivity electrolyte. Okay. So if that means if the resistivity increases, the crevice corrosion increases, because it keeps the anode and the cathode alive all the time. They do not allow them to make them one unit, right, not possible to happen. So this is one of the important parameters in having the crevice corrosion. In fact, people model crevice corrosion, they take this into account in terms of how the crevice corrosion occurs. So in principle, if I give you resistivity, you give all this, I can even find out at which place the crevice corrosion is going to be maximum, right. So these are the things that that happens in typical crevice corrosion of metals. I hope you understand these concepts here. The resistivity of the electrolyte is another important parameter in deciding the extent of crevice corrosion the metal can have, in addition to chemistry of the electrolyte we talked about, right, the pH, the chlorides, and in addition to that the resistivity is equally important. Okay, I hope you follow what I have been just saying. If anybody has questions, no problem. Okay. So that is about the environment, and okay. Now let us look at the electrochemical parameters we have been just discussing now so far, right. Let us look at the electrochemical parameters in general. Okay, let us take this electrochemical parameters. It happens in the passive system, right. So that means you would have now I am going to draw a few schematic diagrams to show how the electrochemical parameters become very important in deciding the crevice corrosion resistance of metals. Okay. This is alloy 1, alloy 2. Now this is the outside the crevice, okay. This is inside the crevice. Tell me what happens. In the case of alloy 2, the passivation potential is lower, not higher. Yeah, the passivation potential is low. It is, or the range over which the passivation occurs is much more as compared to alloy 1, right. Alloy 1 passivates here and alloy 2 passivates here, right. In fact, it passivates even at a more negative potential. Okay. I want to answer from you people. Now this is given this, now we know the mechanism how the crevice corrosion gets initiated, for example. Now what happens? The alloy 1, alloy 2. It is not complex, it is very simple. Yeah, you start telling more and more. I mean, what more you find here in this? You take the case of alloy 1, alloy 2, what difference does it make? If you form a crevice with alloy 1 and you form an alloy with crevice 2, okay, I mean you form a crevice with alloy 2 for example, okay, both are formed as crevices, right. So what happens? Yeah, in alloy 2 what happens? In alloy, see this is the cathodic curve within the crevice, the cathodic curve outside the crevice here, right. So alloy 1, alloy 2. Now you must be easy for you to tell how the alloy 1 and alloy 2 will behave outside the crevice and inside the crevice. Outside the crevice what happens to alloy 1 and alloy 2? Both are passivating, right. Within the crevice what happens? Yeah, alloy 1 will remain in the, will go to, it will go to active region, right. What happened to alloy 2 then? Alloy 2 is still remain in the passive state, right. So that means why does it happen? You look at this now, why does it happen? Well, you know this polarization because what are these things? Use the right terminologies. Yeah, so the critical condensity, right, is a critical condensity, right, IC of the alloy 1 and okay IC of the alloy 2. It's simple, right? It is not even a magic, huh? So it's a simple one. So that means the electrochemical parameter influences. Similarly, what Dorothy has been talking about, suppose if I move this the passive potential to higher and higher, you will see that the crevice corrosion tendency will keep increasing now actually. The ability to passivate at negative potential makes the alloy more stable. So the two parameters that are important, one is IC, if IC increases, what will happen to crevice corrosion? Corrosion? I want a clear answer. Increase, right? Crevice corrosion increases. Similarly, E-passivation increases, the crevice corrosion again increases. You want to make it more and more lower. So the electrochemical parameters are very important in deciding whether the corrosion, crevice corrosion will occur or not. If it occurs, at what rate they really occur. Having said that, the metallurgy are related to each other, right? Then becomes the metallurgy. Of course, the composition. What are the compositions? All compositions that lead to passivation makes the alloy prone to crevice corrosion, right? But the compositions that makes the film stable alloy resistant to corrosion and makes it, and makes it spontaneously passive. If you have all these characters, then what happens? Then the crevice corrosion resistance increases, right. So this general thing we can talk about, right. So those elements which are doing the job, okay, you will be able to see that these things really can happen. So there are certain some empirical rules which talks about this, okay, and you say that elements like chromium, molybdenum, nitrogen in stainless steels and nickel base alloys. Okay, they all help improve corrosion resistance. I just give one example. Three, in all these cases moly content increases, okay, from 1 to 3. Same is true of course with the chromium and also with nitrogen, okay. They all can change the passivation behavior quite significantly, and so if you look at the many alloys, they are developed like, if you compare 316, 304, 316 is better than 304 and 904L is better than 317 and 254 SMO is better than 904L. So 654 SMO is better than 254 SMO. So all these are happening because of modifying the composition of the stainless steels, okay, in order to improve the passivation behavior and more so the critical current density and as well as the overall resistance of the alloy to corrosion. Okay. So, so we have seen now the electrochemical parameters of the corrosion of the metals, and these electrochemical parameters are related to the metallurgical parameters. Of course, they are all related to the environment actually, right. And see, for example, you take 304 and you carry out polarization studies in let us say about 500 ppm of chloride solution of pH 7 and you determine the critical current density, passive current density, pitting potential, all these stuffs, and then you lower the pH from 7 to let us say about 3, you are going to have increase in critical current density, increase in passive current density, and also increase in the passivation potentials. And so it also depends upon the environment as much, okay. So as much as the alloy chemistry. they are all interrelated to each other, and so it cannot be seen in isolation, right? It has to be seen together when you talk about material selection for Crevice corrosion resistance. So if you have an idea about the environment, then you can probably predict you know what kind of materials can be used for Crevice corrosion resistance for a given application. The next thing that we need to be looking at is what is called as the prevention. You can now start your own things, right, because you know the principle and mechanisms, you know the factor controlling the Crevice corrosion. So writing, I mean finding out preventive measures are not that difficult. First and foremost is that we can look at the right alloy combinations. If you can't change the engineering design, or if you can avoid joints such as rivets, flanges, etc., they form crevices, not possible. Then what do you need to do? Go for welding if the design permits. This is the crevice former, right? What else form the crevices? We said about fouling, right? So avoid fouling. Use filters. And if you are going to use a mechanical joints, then you are going to use gaskets. It must be solid, non-absorbent. Gaskets. See, you know about that asbestos, right? Nowadays people do not use asbestos, this is carcinogenic, right? You take asbestos, okay, and you take a Teflon. What is Teflon? It's a commercial name of PTFE, right? What is PTFE? Fluoride, huh? Okay. Polytetrafluoroethylene, right? Okay. So here asbestos, they absorb water, moisture, whatever kind of thing. Here it does not. You can use a sealant, right? If you have a problem, you can go for a sealant. If you use a sealant, then all these gaps can be filled up. This is done in aircraft industries. Use a nice sealant. Well, we can keep adding many kind of variations that you can do. I do not want to spend more time on this because you should be able to devise methods by yourself. I will go to the next method is the testing and evaluation or whatever. I would recommend you to go through this article by R.M. Kane, evaluation of Crevice corrosion. This is an ASM International, ASM Metals Handbook. Volume 13, 9th edition. It is published by ASM International, right? You will also have it in our library. Okay, it's an article by. It's a very nice article, which talks about the complexities involved in designing the crevice corrosion. Now, you need to understand the first of all the concept. What is that here? You have to form a crevice. When I say a crevice, that it has its own geometry, all this crevice gap. So there are several variations that you get, and you may choose a sample which is not flat versus the sample which is quite flat. So do you think the results will be similar? The sample with the flat and sample will become rough sample. Will the crevice attack be similar or different? So where do you think the crevice attack will be more? So the crevice gap, may be more on a much more flat sample than on the rough sample. Okay. So the tight crevice will increase the crevice corrosion rate, and the loose crevice will make the rate of crevice reduced. And I can form a crevice between two metals, or I can form a crevice with a non-metal like a Teflon. So a proper designing of crevice corrosion setup is very important. Okay, the formation of crevice and is one thing. The second is selection of the environment. And you can also look at the standard, ASTM G48 talks about the crevice this thing here. Okay, it is talking about measuring the critical crevice temperatures. Here it talks about measurement of critical crevice temperatures. Okay, and here the solution is 6% ferrichlor solution. The pH is about 1.2. Why do you take ferrichloride? You take ferrichloride because it is a good oxidizer. Okay, it can aggravate, it can initiate the corrosion process much quicker, much faster than simply immersing in, say, a sodium chloride solution. So ferrichloride is a good oxidizer. It is an accelerated test that people do, and generally the temperature they chosen are 22 plus or minus 2 degrees Celsius and 50 minus 2 degrees Celsius, and they expose for about 72 hours. Okay, and then they look at the weight change. It's a simple test actually. What is done here? You can, in principle, you can do set up in any of your own labs, right? What you can do is, see, for example, you can take a stainless steel disc like that. I can have a Teflon disc on this side, Teflon disc on the other side. I can do that. I can have a rubber band holding like that. The rubber band is tight enough to secure, and it also forms a crevice, right. So you have a rubber band like this, okay, this is the steel, this is your Teflon disc. So you immerse in ferrichloride solution and the temperature of your own interest, okay, and measure after 72 hours, see what happens, if there is a corrosion or not. If there is no corrosion, that means at that temperature the material is resistance to crevice corrosion. Now they also made a little bit more sophisticated setup that is called as multi crevice assembly. Okay, where in a single experiment you can have many crevices formed. See here in this case you have only two crevices, right? One on the right and another one on the left you have, but I can also have a multi crevice assembly by taking a Teflon disc and I make various grooves, right. I can just groove like this, I can take this out. See, this is the groove here, right. So I can make several grooves like that, okay. You can make as much as this is called as a plate 2, right. So you can have about 20 plateaus, you can have 20 plateaus, you can have actually, okay. 20 plateaus means you have about 20 grooves that you have, and what you can do, you can take a sample and you can put one assembly here, other assembly here. So you are going to have about 40 grooves. That means you are going to have about 40 crevices are formed in one single test, right. But each of them, this is the crevice, right, this is the crevice here, it is a potential crevice because the liquid can go through this, So here is a crevice here, it's a crevice here. So when it sticks on the surface, okay, and they form the crevice. So there are about 20 crevices formed on one side, one face of it. The other face of the stainless steel sample, we have 20 more, so have 40 grooves are formed, and you can now expose it in the ferrichloride solution, okay, and you can get the attack, done. This is something like an experiment done in our own lab here by one of the PhD students. You see here, okay. Yes, this is the disc now. You can see this here. These are all the attack. These are the attacked portions. See the attack portion. These are the attacked portions because of the crevices. See the attack. Attack is more. And where there is a groove, there is no attack. So this is a groove, there is no attack. This is the plateau region. There is attack. You see here, the attack is on the broader compared to the grooves. Okay. So you see, see here the attack here. There is no attack here. So the crevice has taken place. In these cases, it was done in the lab, and you can see this alloy is 19 chromium, 18 manganese, 0.69 nitrogen. Is the attack is much less. You can see here, you don't see much attack here, 1 or 2, but 14 chromium 8 manganese is attack is quite severe, and 316 the extent of attack is less now. So that means you can able to evaluate the crevice corrosion resistance of the alloy. But here see here it has been exposed only for 24 hours, not for 72 hours actually. So there is no hard and fast rule when you are going to develop an alloy. But then if you are going to follow the ASTM standard, you should strictly follow the ASTM standard. Then only you can compare between the results obtained in the different laboratories now. So these are the kind of things that you can see, and which are very useful in determining the crevice corrosion resistance of these alloys, but it will be very interesting. Now 304 stainless steels can suffer crevice corrosion at sub-zero temperatures. Can you imagine? The crevice corrosion is much more severe even compared to pitting corrosion, other forms of corrosion. So sub-zero temperature means you can imagine that, you know, even below the ice you have some chlorides, the 304 stainless steel can suffer the crevice corrosion. Of course, the time taken for crevice corrosion is going to be more actually. Now, so people use this as a criteria for the crevice corrosion. Now, this is called, people also use term which is called as this is called a crevice corrosion index. So CCI is given as the multiplication of these two, and S corresponds to the number of site attacked, number of sites attacked, and D is the depth of attack. So this is a kind of index people use to quantify the crevice corrosion resistance of the metals actually. Okay, this one more before I close it is the test is electrochemical test. You have known a potentiodynamic polarization curves are obtained, right, the laboratory to look at the passivation behavior of the passive metals. Now, in this case what you do is the specimen what people do in this case, in the specimen you have a crevice here, right. Suppose you have a sample of, here in this case it's about 16 mm diameter, and you have a Teflon, cover this with a Teflon here. PTFE, right, and this is your electrode, and you carry out potentiodynamic polarization. In the anodic side only, not in the cathodic side, anodic side. Do that, and if there is a crevice corrosion, and what is done here, okay. So do a potentiodynamic polarization. And you reverse this, you get like this, okay, and this is called as hysteresis. And higher this, higher the character, higher is the alloy prone to crevice corrosion. So what is done here is here before you do the scan, you hold the sample for about 1 hour in the medium, that will start establishing the crevice actually, crevice corrosion, right, and then scan, anode scan, you do 0.6 volts per hour scan, they do that, and reverse the scan at 5 milliamperes of current. So that means this current is what? This current is equal to 5 milliamperes. Okay. So it is a log I, not small I, because the sample here you have taken what is the dimension of the sample here? The sample diameter is equal to 16 millimeter, right. So, so the current density is going to be different. So this hysteresis is an indication. You compare the different alloys like alloys alloy 276 or maybe 304, and so you compare with that alloy and see how the newly developed alloy performs. 304 of course is not an alloy meant for crevice corrosion resistance. C276 is supposed to be the one of the best alloys from the crevice corrosion resistance point of view. Okay. So this is how we can do that, but you can always have several variations. You can carry out a potential static test, basically you have a crevice and how the crevice affects the electrochemical parameters of these things. So with this, have any questions are there? Anybody has questions? Yeah, see for example, higher the hysteresis character, right? I mean, you can have something like that, right? You can have something like this. Okay, so this alloy is not passivating at all. Look at this and look at this and look at this, and this alloy is more prone to attack. We will see this little detail when you talk about pitting corrosion. Okay, so this the area of the hysteresis you see here, as increases, the alloy becomes more prone to pitting corrosion. I am sorry, yeah, pitting corrosion as well as crevice corrosion. Anyway, they are not. I mean, you will find later that the alloy is resistance to crevice corrosion would also be resistance to pitting corrosion as well. Okay, so. Okay, so with this we will close the discussion related to crevice corrosion, and yeah, let's see. If you have any questions, think about it. In the next class when we meet, we will discuss on this topic.